Hi, I'm Bob. Welcome back to 5 Minute Econometrics. In this program, we will explore fundamental econometric concepts, estimation methods, and identification strategies. Today, we will talk about the issue of measurement error. Both the outcome variable and the explanatory variables could be affected by this problem, which often arises in survey data. When we collect data for the variables in our model, it's common for this data to contain measurement errors. For example, in a model that connects annual income to education, health status, age, and gender, survey respondents may struggle to accurately record their annual income from the previous year. Additionally, the self-reported health status may be imprecise, and occasionally, even the age variable can be misreported. The measurement error is defined as the difference between the observed value and the actual value of the variable. We will first examine the consequences of measurement error in the outcome variable for ordinary least squares estimation. Here's the scenario where only the outcome variable is measured with error. Let y star denote the true outcome variable in our model. Let y represent the observable measure of y star. In our income model, y star refers to the actual annual income, while y is the reported annual income. We anticipate that y and y star will differ due to memory limitations. The measurement error, E0, is the difference between them. To find the connection between the true model and the estimate model, we plug the expression of y star into the true model. The error term in the estimate model, epsilon, is the sum of the error in the true model, mu, and the measurement error, E0. We assume the error term in the true model, mu, is not correlated with any explanatory variables in the model. We also assume that the measurement error in the outcome variable, E0, is not correlated with the explanatory variables in the model. Generally speaking, this assumption is reasonable. Think of our income case. The error in the reported annual income by the survey respondents should not be systematically affected by the respondents' education, health, age, and gender. As a result, the error term in the estimate model, epsilon, which is the sum of mu and E0, should be uncorrelated with the explanatory variable. Therefore, the OLS estimates are unbiased and consistent. In unusual cases, the measurement error in the outcome variable could be correlated with some explanatory variables in the model. This model examines whether receiving a job training grant reduces the scrap rate in manufacturing firms. The firms that did not receive a job training grant should not have an incentive to over-report or under-report their scrap rates. However, the firms that received a job training grant may have an incentive to under-report the scrap rates because they want to make the grant look effective and hope to receive the grant again. If this is the case, then the dummy variable grant will be negatively correlated with the measurement error in the reported scrap rate. In other words, when the explanatory variable grant increases from 0 to 1, the outcome variable will be reported systematically lower than the true value. We can prove that the OLS estimator beta 1 hat is downward biased. Here is the proof. The expected value of the second term is 0 because of the zero conditional mean assumption for the true model. The expected value of the third term will be negative in this case. It produces a downward bias in beta 1. Since beta 1 should be negative, a more negative estimate means the job training grant program seems more effective than it actually was. The second property of the OLS estimates under measurement errors in the outcome variable is that the variance of the OLS estimator becomes larger. The variance of the error term epsilon equals the sum of the variances of mu and E0 if mu and E0 are uncorrelated, which is larger than the case without measurement error. This leads to larger standard errors of the error term. From the formula, we know that the OLS estimator's standard error will become larger. As a result, the t-statistic for the OLS estimator will decrease in absolute value, and the explanatory variables will be less statistically significant. To offset this inference, we can increase the variable's variation SST by collecting more data, and decrease the R-squared by avoiding severe multicollinearity among the explanatory variables, as the OLS estimator standard error formula shows. Today, we discussed the properties of the OLS under the measurement error in the outcome variable. The OLS estimate remains unbiased and consistent, provided that the measurement error is not correlated with the explanatory variables, which is usually assumed in econometric analysis. The variance and standard errors of the OLS estimate will become larger, making the variables less statistically significant. However, this is generally not a concern in applied econometric research. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.